Okay, well then, third session today, linear optimization, linear programming. Okay, so the food will come roughly halfway through at 6:15. We're going to have a break, and then we're going to start again. I don't exactly know where I'll be or not at this time. This will probably be pretty useful if you still haven't done the assignment. It will probably cover most of what you will need to know. Well then, okay, let's get started. And there will be a very little part of things you perhaps have not seen before. So today is all about linear programming. So the problem, the standard problem would be you want to maximize this function such that and x positive. So you have seen this a million times, or at least 1,000 times. So this is the normal formulation that you can always extend to what is going to be of interest to us. Max C transpose x such that AX equal B with x positive. You can go from this problem to this problem through the use of slack variables. If you want to have a quick reminder, basically the constraint sum of C A. Well, no. Okay, let's even put it properly. AIJX. This constraint can become inequality through some AIJXJ plus dy. No, let's call it S for SY for slack variable equal BI. So the first thing I wanted to talk to you about is linear programming, as you have seen in the course, is really highly related to the simplex algorithm you've seen. The simplex algorithm is some kind of method that allows to give you the optimal value. However, where does it come from? Why would pivoting on some rows and doing these things actually work? So I would like first to introduce a more general framework, which is called the reduced gradient. Something you also perhaps have seen in CME 304, well, Walter's course. So let's suppose you want to minimize f of x such that ax equal b and x positive. An optimality constraint that you may or may not have seen. So x star is an optimal value, implies, among other things, so okay, so you have this function in some space, and you are, in fact, when you look at this, you are only interested in a subspace. For example, if your function is in 3D, you might be interested in the value of f only in the plane, and this is the plane ax equal b. What interests you is that you can think the problem as, oh, I'm just going to work on this particular plane, and instead of working with the gradients of f and doing some optimization, I am just going to work with the reduced gradient, the gradient in this particular subspace. The thing is that this optimal, if you consider in this setting that you've got a basis B. Basis B and the rest is n, how can I say? This is somewhat a partition of your space between the basis and the rest of the basis, such that, how can I say, B being a basis of your constraint. The nice thing is that if, how can I say, the problem only in fact depends on the non-basis. What does it mean? It means that I really have a partition of the space in. I really have a partition of the space in the basis and the non-basis. I can write x equals xb plus xn, a equals ab plus an. This being a full rank matrix, c equals cb plus cn. You have the relation xb equals probably something along the lines of, forget all the time. Oh, where are you? B minus A. So in fact, what I wanted to tell you is that you do not exactly live in the full space. What happens is that you just fix some of the variables, and on the basis, xb is entirely defined. So as you can see, xb does not really belong to the problem. It's fully constrained. You just need to work on this thing. And this is the full parameter. So if you consider that, in fact, you do not want to minimize f of x, is the same thing as minimizing f of xb xn, which is the same thing as, because xb is fully constrained. It's some kind of other function of xb. It's let's call it g of x of xn. So this, I just wanted to express the fact that the problem does not depend on xb, it only depends on xn. And well, let's keep that for the moment. What's nice is that I did put some optimality conditions, which are sorry, just a moment. If you remember the first order the first order optimality constraint I gave you, they are exactly equivalent to, you can prove it, and this, if you may remember, is you have to understand that what it means is that these constraints are the standard constraints. When you think only in the subspace, these are standard optimality constraints. And the thing I gave you with this constraint and the other one, if you remember, time times x star equals 0, these are equivalent. So you can, oh yes.
You're missing a parenthesis, third line from the bottom.
Sorry, on
third line from the bottom.
Oh yeah. No, not this one. Well, at least this one. Up. Yes. Yes. Sorry, my bad. The whole point of this explanation, is that for the general case where you want to minimize f, not just a linear constraint, there are some very simple algorithms which can be described in 6 steps, and you'll see that these steps are like highly similar to what the simplex does. First of all, okay, I'll just write it down. So for the radius gradient, first of all, like the simplex method, you start with a feasible point. So nothing incredible. Second part, you find a partition B and N such that basically xb is strictly positive. This particular basis is called a non-degenerate basis. Then you check, you compute the radius gradient. As you can probably guess, the radius gradient of a linear function is particularly simple to compute. This is why this step in the simplex algorithm does not exist. It's like trivial. For a step, you check if you are an optimal point, check optimality with the two equivalent optimality constraints I gave you. If not, if it's not optimal, it means that you have found a descent direction. And you just need to compute some step. If you remember, some kind of xk plus 1 equals xk plus. This is the step length, and this is the direction of descent. So this is a scalar, and the direction of descent is some kind of vector. And then you repeat. The thing is that when you will repeat, you will have to find a new basis. So the simplex method is just the very simple case of the reduced gradient algorithm. It happens that in reality it was discovered the other way around. The reduced gradient was introduced afterwards, but how can I say? This is a very logical way of having an optimality, an algorithm to find maxima or minima. And the simplex method just happens to be very efficient because it performs these actions extremely efficiently, especially for double thing. Okay. So rest assured, this will probably be the only thing you haven't seen before. So, I wonder in what order I'm going to. Some basic theorems theorems or properties you may need to remember. A feasible point. A feasible point is just a point x such that ax smaller than b and x positive. Also, you have to know that the set of feasible points is a polyhedron. It's by almost definition. It's a polyhedron, so basically just an intersection of half spaces. And it happens to be convex, like all polyhedron, which again is a useful property. A property that is useful, yes.
Do you mean that all the feasible points are on the outer edge, or
this is just like the border, but no, the feasible points include also the inner points of the polyhedron. You never need to. This is again why the simplex algorithm simplifies a lot of things. You are not interested in interior points because some properties of this ensures you that you are not interested in the interior of the polyhedron. You're only interested in the border, and even more than that, in the extreme points. A basic feasible point is a point such that you can you can write it x equals xb xn is a point such that you can, if the dimension of your space is n and the dimension of your constraint is m, a is of rank m, you can have n minus m zeros. Yes, at least. And you would call it to be a degenerate basic feasible point if you have n minus m plus 1 zeros, at least. So n is the dimension of a big space, the space you're working on, like X, basically. No. And m is the rank of the matrix A.
Sorry, is it Ax equal to B? You are working on?
Oh, No, right now I have AX, sorry, I was considering only AX smaller than B. If I have AX equal to B, okay, so your polygon is flat first.
You're working on AX equal to B, then you set xn equal to 0, then get xb. Otherwise, you cannot get xb, right? xb is not determined. If it is not equation, it's inequality. So you divide x into xn and xb.
Yes.
You mean xb is determined by xn?
Yes.
Then it's from ax equal to b, not ax less than b.
Yes, I agree with you. Yes. No, you're right. Okay, and I believe I am done for just the names, definitions of properties of things. And now, how do you actually solve? How do you actually solve a linear program? Up. So I have tried to pick an example that you probably haven't seen before.
I had a couple questions on that before you raised it, but does a basic feasible point always exist?
No. In general, linear program has three possibilities. Either it's totally infeasible, no points, check the constraint. Either the problem is unbounded, or either you do have what interests us. Actually, you have a solution that is somewhere in one of the action points of the polyhedron. But no, you don't necessarily have a basic feasible.
And I'm still not following the argument of why you changed the definition of feasible points from ax less than or equal to b to ax equals b. It seems like it should be less than, just based on the problem definition, right? We're solving x less than.
Yes. Okay, so the first thing I could say is that basically, if you want to solve ax smaller than b, you can always change it to ax equal b by adding slack variables. So ax smaller than b being a smaller problem than ax equal b, you can, if you can consider general case with ax equal b.
Then we're restricting our set of feasible points. Then it seems like
We are.
by requiring that they're equal to b. Yeah.
No. Oh no, you're not at all. No, because you extend the matrix of constraint. Once again, every time you have a problem like I don't know, x smaller than 3 can be changed by, and x positive can be changed by x plus s equal 3 and x s
Yeah.
positive.
You didn't write in the slack variables before, so I guess.
Oh yeah, sorry. It was it was the form ax equal b being the standard form. It's assumed from that point on that every matrix, except if it's especially stated that it's not the case, but in general, it's all ax equal b. So you want to max, okay, x1 plus 2x2 minus x3 such that it's highly advised that you take a pen and paper, you write the whole thing with me. Probably be useful when you try to remember how you actually solve the problem. Okay, now let's write the whole thing.
Is it a z or is it a 2?
Excuse me.
X1 plus 2 x2?
Yes, sorry. No z's, only 2's everywhere. Okay, you want to maximize this such that this is verified. You, of course, never want to write this again. So you're going to say that the matrix A is 2, 1, 1, 4, 2, 3, 2, 5, 5. B is equal to 14, 8, 28, 30. And you have AX smaller or equal than B. Exactly as Austin said, you do not want to see this problem. There are inequalities. You are going to introduce slack variables. And you are going to expand a bit this matrix, and now your matrix will look like this: 4, 2, 3, 2, 5, 5, and 14. AX equal B. Now you have AX equal B. I am going to go from this matrix step by step to the solution of the problem by using the simplex algorithm. So let me erase this first. We are going to put all these values in the tableau, including B, which is 14, 28, 30. And we are going to put what we, so you can see these are the variables you have, so x1, x2, x3, slack 1, slack 2, slack 3. We are going to put what we want to maximize. So we want to, and let's put on the side, this is variable. So this is x1, x2, x3, slack 1, slack 2, slack 3, and z. So what I'm telling you is that you are not going to maximize x1 plus 2x2 minus x3. You are going to maximize variable z, and you are going to add a constraint, which is x1 plus 2x2 minus x3 minus z equals 0. How wrong am I wonder? Just want to tell you, there might be a minus somewhere. I'm not entirely sure. It doesn't really affect the problem. This is just for your understanding. The part Z and everything here can be forgotten in the implementation you're going to do. I want it to be here so that you understand what's actually happening. So the first important thing to note here is that in this matrix, we are lucky. We immediately can find a submatrix that is identity of rank 3. You can see that it is here. This is a matrix. This matrix is going to be extremely important, or this submatrix is extremely important. You will need to have it at each iteration. Yes.
So let's see, what all is considered part of that matrix there? Are those little numbers you added along the bottom, are those part of it, or is that?
Sorry, yes. Only in this part of the matrix are you interested in having identity.
Okay, but are we dealing with that whole block of numbers as one matrix, or?
You will treat the whole block as one matrix, but you're only interested in submatrices of full rank identity here, and in this upper left part.
What's the little -1 hanging out to the right?
It's because there's a hidden variable, which is z, which is, you can see, it's x1 plus 2x2 minus x3 minus z equals 0. So you can see, this is, you agree, this is a constraint on the matrix, which is 2x1 plus 5x2 plus 5x3 plus s3 equals 30. And there is, just for educational purposes, this one is going to be left out of the actual thing you're going to compute. So this is why I put it to the right. There is an additional variable z, and what you want is you want to maximize z, and then or z. Do you say z or z here? Z. Okay. When you maximize z, you're going to actually find the optimal solution, what you're looking for, and this will hold the value. But when you will program, this will not exist. I'll just put it so that you, yeah, -1.
Bertrand, just to make sure I'm clear, you're introducing this z to be equal to the stuff on the left here, right?
No, okay, so do you agree that each of these lines represent a constraint? And I'm going to add another constraint, which is x1 plus 2x2 minus x3, which is like, no, oh yeah, minus z equals 0, equals 0. So here is the identity submatrix here. How do you use the simplex? So the first thing you do is you find a column here which has I should have explained it. You find a column which has a positive value here. So it could be this one, it could be this one. You can pick whichever you want. I don't know for what reason I chose this particular row. And you say you're going to pivot on that particular column. Sorry, choose this column. Why is it important? Because you are trying to maximize it, and basically, if you can crush this down to 0, you're going to increase the value of z. Then you need to choose one particular row among these 3. So you forget all the line, you choose a column, you choose a row. The choice of the row is extremely important. You need to choose a row such that, that's the problem of skipping, sorry again. You have an identity submatrix. Why is it important? It's important because it tells you where you are. As you know, the simplex algorithm, you are iterating through extreme points of the polyhedron. You have polyhedron, and then you move along edges. However, where do you know where you are? You know it because of this identity submatrix. In this identity submatrix, this corresponds to certain variables. This means that you've set 0 to all the other variables, and then so these ones are, this is xb, and you know what xb is equal to something. It's ab minus 1, b minus a and xn, I believe. So here you have a point. When the matrix will move around, you'll have other variables, but the identity submatrix tells you where you are. And the nice thing is that when you're going to pivot along one of these points, you're going to in fact choose an edge. And what you're interested in is, if you are here, and for example there are several edges, you want the edge you're going to end up to verify x positive and s positive. You want the point to be feasible. And there is one extremely simple rule to ensure that the point you're going to end up is feasible. I believe it's called the blend rule. I'm not entirely sure. You're gonna compute the ratios. So on this column you have 1, 2, 5. So this is the second column, and you wonder which one of these you will choose. You will make the ratio 14 divided by 1, which is 14, 28 divided by 2, or 30 divided by 5. So this one is 6. And you will take the minimal one. Because you will pick the minimal one, you will know that you will end up in a feasible point. And that's an extremely important thing. Otherwise, your algorithm doesn't work. So what does it mean? 2 steps. First, you choose a column with a positive value, and you choose a row that has the minimum ratio between these two. So you're going to pick this point. Here on now, it's pretty simple. You're going to do 2 operations. First, you're going to normalize the row. You're going to divide it by the value that's actually here. You have to notice this one obviously cannot be 0 in a way, otherwise its coefficient would be infinity and you wouldn't choose it. You have a question?
Yeah, so what happens if you don't have a positive column? Like if you are maximizing negative x1 minus 2x2 minus x3, whatever.
Unwanted.
So then you are already at the optimum.
So unbounded case.
I'm kind of wondering which case we are right now.
No, I think because you take the minimum, you take others, right?
You should take the
Because you're taking the minimum, now you're taking 6. If it was 0, it would be more than 6.
0 vector is optimum.
So if, let's say, if one of them is missing, right, that's the question. If x2 is missing from the equation, so you have a 0, 4, 0, 3.
Yes.
So when you divide the b2 over 0,
yes, it's infinity.
Yeah.
Hmm.
So you will not choose it, basically.
I kind
I think what he was asking is if not the constraints, but the actual optimum.
Yeah, no.
So if you don't have an energy,
Okay, so the things I can say, because I believe I won't be too mistaken, is that hopefully this situation does not arise because some black magic behind. Now, what is the exact black magic behind? So I honestly do not know. What may be several reasons. It may be that if you have zeros, this means that somewhere your matrix of constraints is not full rank, perhaps. I had another potential idea, which is, so why does it not arise? Of course, it does not arise in the example I give. How come?
I mean, I think my question was a little bit different. If that's, I don't know if you're still.
So your question was in the row, if one is negative.
I mean, there's step 1 and step 2, and step 1 is find a positive, like a row that's positive in that bottom. Well, find a column.
Column was a positive value, yes.
Yeah.
And the second part is you find a minimal ratio. And what happens if there's a problem with the ratio?
No, my question was the first one. What if there isn't a positive column?
You're optimum.
The less line.
Oh, sorry. If there's no positive. Oh, excellent. No, sorry about that. Much simpler. It is this one and the solution. It means that you are at the optimum. What does it mean? You're trying to maximize. Minus. So these are x. So you're trying to maximize something like sum of alpha I xi minus z equals 0. You want to maximize z, and if all of these.
Hey, Bertrand, can you step aside a little bit?
We can see right now.
Yeah.
If you want to maximize this particular thing, and all of these are negative, you do realize that in fact you have reached the optimum. I mean, yes, you just put zeros everywhere. And,
But I guess just the issue that 0 may not be feasible, right?
No, but that's the nice thing. You start with a feasible point, which is a problem itself I will talk on later, but then you will always be at feasible points. So the nice thing is that when you reach one particular point through some iterations on the simplex, you will always be at a feasible point, and if you have only negative values, you just put zeros on all these values, and you can maximize z and gain your optimal. So your question is, if everything is negative, you've reached the end. So the whole goal is to iterate until everything is negative. But I do agree that I still stand. If there are problems about the minimum, I'm not so sure. It does not happen. Okay, so once you've chosen the pivots, two things. First, you normalize the row. So you do everything, basically, you divide this all these values by 5. And then the other thing you do is that you do some linear operations so that all of these become zeros. So for example, here this once you will normalize the thing, this row you will take this row minus twice this row so that this becomes a 0. So you zero out the column. The result. So first, I will start with the third row because it's the one that is normalized. So it will be 2/5, 1, 1, 0, 0, 1/5, and 6. Then I can put out the other rows that I can compute 6 divided by 5, 8 divided by 5, 0, 0, 0, 1, 1, 0. Here there's the little z with a -1. No. Yes, -1. Okay, so now that it's become horrible to understand, here is your new tableau. First thing you have to note is that through this operation, you have a new identity submatrix. So comprising now variables x2, and the first two slack variables. This, once again, tells you where you are on the polyhedron. Basically, you set 0 to all the other variables, and then you can compute xb equals something matrix inverse blah blah blah, and you get where you are. The other thing that is nice is that in general you would not know whether it's a feasible point, but the algorithm and the choice of your pivot ensures that you are a feasible point.
Question. So you said normalize row and zero out column, then how did everything else in the matrix change?
So here this row is normalized in the sense that I divided everything by 5 so that this particular pivot becomes 1. So 2/5, everything is divided by 5, nothing transcending.
Sorry,
now,
divide what by 5? Divide
the whole
row.
The whole row, so that it's normalized so that the pivot you used now becomes a 1. And as you noticed, it is even a part of the identity submatrix. Then what you do for every other row is that you zero the value in the column pivots. So if by doing linear operation, which means, for example, here there was a 1, so I'm going to subtract from this row the new normalized thing only once. Here I'm going to remove it twice so that it becomes a 0, and you can actually check here it's 2/5. Yeah, 2 minus 2/5 is 8/5, and you do have the actual value. You do the same thing for the values everywhere. And what you note is that now you have somewhat, well, all the constraints are a bit different, but this one is interesting because you do have, well, your z that you're trying to maximize is now equal to something different. However, you can still keep on doing the algorithm. Now you're going to choose a column with a positive value. It's going to be pretty simple. You are going to choose a pivot. So you take the minimum ratio. Here, 8/5 divided by 8, 1/5. Oh, 1/5. And something probably not interesting. So what interests you is that there's a tie between these two. It's strictly not important which one you choose. When you make the minimum ratio, the two ratios for these two rows are the same. You can pick whichever you want. I decided to pick this one.
One more question.
Yes.
So again, when we're picking the positive element from the last row, are we allowed to pick positive element from the entire last row or just from the first 3?
Oh no, from all of them. It's the slack variables are no different from the standard variables in this problem. They really is just the name, but
okay. So without the zeros in the first matrix, it was a little confusing.
So
it was because the constraint is sum of this times the variables equals.
Right. Does it theoretically extend even past the slack variables, like the other 0 or 1?
Excuse me?
Well, so can you? So I'm not even sure if it's possible, but suppose that that like in your dot matrix there's the 0 and the -1 on the right bottom. Are those potential?
No, because you must pick. Your pivot will always be on one of these. How can I say? Here you have 0, 0. Each time you pick a pivot in one of this thing, so you 0, so it changes, and then you change each row by adding a certain times the row on the pivot. The thing is that as they are always 0 here, the thing is never going to change. Is it what you asked for?
Right.
The -1 is always going to be the same, and z is always going to be equal to this linear combination. Now it's this linear combination, but it's the same.
Okay.
Just a moment.
So to make sure I'm following.
Yes.
So when you're choosing in the bottom row, that positive element.
Yes.
You're choosing a direction that can maximize your function and make your function go up.
Yes, absolutely.
And if you happen to choose like the biggest one,
Yes.
right, then you're choosing the one that at the moment is greedily making you go up the most,
Absolutely.
right?
Yes.
And then when you're doing the row operation, you're basically saturating that variable.
Exactly.
Right? Going as far as you can in that direction.
Yeah, well, you go into that direction until you hit
another constraint.
Yeah,
right?
absolutely.
What the basically optimization.
Yes, absolutely.
And then you get this new optimization problem, right?
Mhm.
Because all your optimization constraint, rather your objective function now changes.
Yes.
Right? But I guess I just want to understand in the new transformed optimum you've written, you now introduce this -12 under the constraints.
Oh yes.
What does that correspond to?
So the thing is that, so what does it correspond to? It corresponds to minus the value you're actually looking for. What does it mean? Here on this constraint, you had something like x1 plus 2x2 minus x3 minus z equals 0. And the thing is that I believe, yeah, you set all of these to 0, so z is going to be equal to 0, this constraint. Here, on this new problem, you have some kind of sum of your variables. So it's xe or, variables. Minus z is equal to minus 12. Because this is, once again, you must see it as a full constraint. And now, z can be equal to 12. You do here, in fact, in this particular vertex, you are on your polyhedron. Now the value of the optimal solution is 12. And basically, this is just a way of keeping track at each iteration on what is the value of the optimal, what is the value of the feasible point you are in.
Oh, I see. Okay.
So are you subtracting the pivot row from everything else to zero out that column?
Yes, absolutely. So even this one. So this one I removed. If it was asking, in this row, even in the row of the result of what you're trying to optimize, you are going in this example to remove it twice. This particular row. Is it what you're asking for?
I think so. Yeah. But so secondly, is that what's the smallest ratio you're looking for? Is it which one's on which side?
You take
Like
14 divided by 1,
oh, okay, that right.
28 divided by 2, and 30 divided by 5. And you can think of it as Ryan said, when you go down this particular direction, which of the constraints are you going to hit first? And by picking the minimum, you can check that actually. So I picked this row because I thought that it was this constraint, that is going to be, this constraint that is going to be hit first. And actually, yes, there's a 0 that pops here. You can see, in fact, you have switched this with this. You were on certain vertex, and you are going to switch variables. Remember, so certain variables are set to 0, and the other one are computed immediately. And you know which variable you're going to replace by doing this minimal ratio. Okay, so the equals, and then if I do it once more, so I'm going to run out of space. Anyway, you know. I'm going to do it exactly once more. So if I pivot on this particular thing, I will output the full matrix so that you can actually check later on that I was not doing things wrong. So the first thing you know, there must be a 1 here. And 0, 5, 16ths, 0, 5, 16ths, minus 1, 8, oops. Once again, you have normalized the thing, so you divided everything by 16/5. And then you have zeros the column, so you put 0, 0, 0 here by subtracting a certain number of times this column from the rest. And now you have obtained another linear program. However, what interests you is that you want to maximize basically some kind of sum of alpha A and xa or SA minus z equals minus 13. All of these are negative. And you know that all the x's or s's are positive. So from this, you can automatically derive that z is going to be smaller than 13. However, in this particular tableau, you have z equal 13. So you did find an optimal solution. So yeah, the full point is the full point of the tableau is you have introduced some z that happens to verify some constraint. You're going to iterate over the edges, change the linear problem until you reach a problem that is really trivial to solve. You want to maximize something with only negative values here. It's obvious that that this is a feasible solution and the optimal solution. So you found a feasible optimal solution. Plus, once again, you have an identity submatrix, which means that you, how can I say, you really you know which variables are set to 0. So this is also a basic solution. So you have found a basic feasible optimal solution. You can also verify a few normal things. I mean, here you had before you had this, and this variable as you know in the the 3 in the optimal. You had the 3 in the optimal. In the identity submatrix, and you decided to pick this pivot, the second one, and in the second row intersect with this variable, and this is the variable you're going to put out of the this is the variable you're going to put in the identity submatrix, and this is the variable you're going to put out. It's kind of logical. You have an identity submatrix. When you pick a particular row, it's going to intersect the one of the submatrix somewhere, and this is the variable you're going to put out of the identity submatrix, and the variable you picked, the pivot, is the one you're going to put in. Do you want an explanation, or was this very obscure? Okay, seems fine.
So the reason why, right, is because that variable saturated, and now you're saturating this one, you're forcing that one to sort of out.
Oh yes, yes, yeah, it is this one, and you check that actually when you saturate it, you are still feasible because of the mean ratio thing.
You also explain the ratio test that you are doing to choose which row. Are you really just taking the ratio of entries, or are you taking like absolute values?
I do believe I'm taking just the ratio. Now you may wonder, oh, but is this ratio always well defined? What happens if I want to divide by 0, or what if the value is negative? And this is what I was saying to Matthew, which is, I know it works. I don't exactly know. I don't know why it doesn't fail. I'm very sorry about that. It has to do with some black magic under the algorithm that I am not entirely familiar with, and I'm sorry.
I think you want to pick a row that's where the right hand side is strictly greater than 0. You can end up with negatives on the right hand side, and I think that would just be going in a direction that is immediately infeasible.
Yes. Yeah, when I think, yes.
Right, so you pick your column, so you know what direction you're heading in, n space.
No, absolutely.
And you're trying to pick a row to know when to stop.
Yes,
and
that's exactly that.
Well, what's my closest one? So what's the shortest distance I can go in that direction?
Well,
a negative distance is technically shorter than a small positive distance, but it means that you're going infeasible.
Yes, no, you're absolutely right. This means that if you go 6 units in that direction, you're going to hit the thing, and it's the smallest one. But you're right. If it's negative, it means that you are already in the wrong. I mean, if you go immediately, you're going to be infeasible.
Where are the xi and the
okay, they never move. So this is x1, x2, x3. This is s1, s2, s3. And then if you want to know the actual values, you put zeros outside. So x3 equals 0, and s2. I'm just thinking, is it really this one that you put 0? Just want to be very sure. You put zeros. Yeah, you put zeros out. You put zeros out the basis, and then here you've got here this is the basis, and you know that you can compute xb as a function of this is xn, and you can compute as a function of xn.
Okay.
They might honestly, there might probably be a very simple way to know which of these are there inside the Tableau. I just know that you can find them. Does anyone who actually did it know where they are?
So if you find the 1 in that column, so for example, in x1 it's in row 2,
Yes.
you walk all the way to the right, x1 equals 5.
Oh, well, probably. Yeah.
Yeah.
Probably. Oh, yeah. It's kind of obvious. Yeah, if x3, s2, and s3 goes 0, so here you've got 1 equal 1 plus a lot of zeros is equal to 5. You probably get an idea of where you can get x1. Sorry, thanks for the answer.
I have another question. So I still don't quite understand how the feasible point is baked into the Tableau. So say we want to maximize, in the initial problem it's maximize over all coefficients are negative. And so by the original...
Sorry, in the original...
So if our maximization problem, let's say, is negative x1 minus 2x2 minus x3.
Yes.
And then by our algorithm, we wouldn't do any steps, but
Yes, of course, because you have to remember, you want to maximize minus x1, minus 2x2, minus x3.
Okay, so in that case there's no
x1,
solution
x2,
whatsoever.
x3 positive. Yeah, the solution is
Okay, I
zero,
see.
zero.
Sorry.
No, it's
Because ax has to be greater than b, is the other. So this says that there's no solution whatsoever.
No, the solution is 0, 0, 0.
Yeah, then ax is not greater than b. So it's infeasible.
No.
Well, it's less than or equal to b.
Yes, it's
So, and b has to be positive.
The problem is ax equal to b if you add the stack variables.
I see.
So you have x1 plus s1 equals like what was the actual value? Probably 14. Yes, so you have x1 equals 0, s1 equals 14, and the actual solution of the problem, which exists in feasible, is 0, 0, 0. If you put everything
Sorry, what were our x values again?
what the x values again?
Yeah.
So in the Tableau, once again, I mean, here, you remember, so this was the standard matrix of constraints when you had ax smaller than b, so this was really a, and this was b. And if you look at it this way, here this is really the column of x1, because it really means when you multiply it by the vector x1, x2, x3, you really get the constraints back. So really, so these constraints, and they never change. I mean, this is really this is variable x1, x2, x3, s1, s2, s3. Is it what you're asking for? Not at all.
Maybe.
So
So we have this table at the end here.
Yes.
How do we get x1, x2, and x3 out of that?
Yes, absolutely. So the first of all, identity submatrix. Everywhere else is 0. So for example, this is x3, and x3 is equal to 0. It's probably no, it's not written anywhere. S2 and S3 equal to 0, but you're not really interested in those. And then how do you get x1 and x2? As Victor said, you can get it by just reading here, because here the constraint, when you look at it, it's x1 plus something x3 plus something s2 plus something plus a linear combination is equal to 5. However, for all of these, you know that the coefficient is equal to 0. Once again, it's outside the sub-identity matrix, so it's these 3. And you know that for all of these, the variables are going to be set to 0. So you have x1 equal 5. So it's pretty easy to get x1. I suppose this answers your question. Okay. Well, I think it's time for a break. Was it? Yeah, it's time for a break, and then we're going to have a short, probably 15 minutes about the dual just after. Thank you. Okay, so this part will be pretty short. First of all, I had something to say about the ratio. So as you remembered, I told you to, like, if this is the column of the pivot and these are the value, I told you to pick the one with the minimum ratio between 14 divided by 1, 20 divided by 2, and 30 divided by 5. And I had the question, for example, what happens if I have a minus here? And as Scott said, if your ratio is negative, you should ignore the row. What does it mean? When you and also, as you can suspect, when you have a 0, because in both cases it means roughly the same thing. When you take the ratio, you're wondering, if I change this variable, how far can I go before I hit the constraint? If, for example, here in this case, when there was the 2, it means this was the smallest ratio, meaning that you're going to hit this constraint first. If you have a -2 here, it simply means that the more you add, in your ratio is negative, the more you add to the constraint, the less you are likely to hit the constraint. What does it mean? It means like basically you have the constraint, like x2 it must be smaller than -2. And it's obvious that if you increase x2, you're never going to reach the constraint. So you can walk an infinite number of times. So this is not, by increasing here, you are not going to hit the constraint. So this is not what you're looking for. What you're looking for is the first constraint you're going to hit. So this is what you can ignore. So yeah, this was a remark about the negative ratios.
So if it's negative, then it means the maximum is infinite. You don't have.
No, it does not miss it. If
the right hand side,
it's not because you have an infinite direction, when you can go infinitely far, that your maximum is unbounded. Let's suppose you want to maximize minus x2, and here you have the constraint x2 can go to infinity. The maximum is still bounded.
When you pick the pivot, the coefficient is positive.
Yes, you're right. Yeah, the coefficient
then
is positive.
it goes to infinite, then it's unbounded. Then the problem is already solved.
I believe you're right. So this probably is the magic I told you. If the problem is here we're considering the feasible case. If the problem is infeasible, you will hit one of these problems.
Can I say we want to choose the minimum ratio because we want to keep the column on the right positive?
Also, yes, you're keeping the column on the right positive.
If this is
yes, yes, absolutely. Well, you pick it. You're right in the sense that, as I told you, you're going to pick this particular pivot, the smallest one, so that you keep the right-hand side positive, and it's equivalent to keeping the point feasible. So you're right.
But so you're assuming that you're starting with the right-hand side totally positive, right? And
otherwise you can times -1 and it will be positive.
Yeah.
Yes. Oh, good notice. Yeah, you can just minus the whole thing if it's negative. No, would it be? No, yes, I believe you're right. Another small note about the the trouble you may encounter when you code thing. As one of you pointed out, when you zero out the columns and do some operations, zeros will appear normally. However, not zeros will appear. So, I mean, you remember when you pivot on this column, so you're going to put zeros here and here. So there will be no problem with your computer algorithm. However, if because here there was a 2 and here you have a this is a 1, so here you have something like a 2/5. This is going to be zeroed. However, not because you're going to say 0. You're going to make really the operation 2/5 minus 2/5. And you will probably, in fact, have not a 0 in the actual tableau. So what you should check out is that basically when you will check is the tableau is equal to 0, it will happen in your code. You should check whether it in fact is smaller than a particular value. Let's say 10 to the power minus 8 because I don't know, it seems like a right number, does it? Okay, so yes, this was just be warned, these problems will appear in the problem. And also, the other problem is that in the tableau I gave you, you start with a feasible point 0, 0, 0. Finding a feasible point is a problem in itself. However, the nice thing is that finding a feasible point of a linear program can be solved by the simplex algorithm. So you can solve the simplex algorithm with the simplex algorithm, which is a really nice thing. However, the good thing is that you can solve this particularly easily. What do? You introduce. So this is start with a feasible. You add one extra variable. Let's call it t. So there is a x, there is s for the slack variables, and there is t. You are interested in another problem. You are interested in minimizing t such that ax plus s minus t times the vector 1, 1, 1 equals b. Why do you want to do that? So remember, your problem was ax equal b. If the b's are positive, yes, so extended with slack variables. If one of the b is negative, which will happen in the homework, you cannot just say x is going to be equal to 0. Otherwise, your starting point will not be a feasible point. Really, the problem appears when one of the bk's is negative. So here, the point is that if you consider this particular problem, first of all, I'm going to tell you that I can find a feasible point pretty easily. I'm going to set x is going to be equal to the vector 0. And then I'm going to set t is equal to minus the minimum of the bi's. And so it will be equal to a particular minus bk. And then now I can tell you probably that sk is going to be equal to 0. So I have set all these to 0. I have set this one to 0. I still have remaining m variables, and you can compute this xb as a function of xn. You can check that this is actually true. I mean, you put t equals minus bk so that it exactly works, so that sk is equal to 0. Yes.
When you say t equals minus bk, are you saying t is a scalar still here, and bk is the argument of that?
Yes. So yes, there's a particular k.
Okay, so I think that not all of your sk will be 0 in that case, because you don't know that all of the bk are the same, right?
Sorry, all the sk.
If you're guessing that all of your x are 0, then what you have is...
No, I'm stating that all my x are going to be equal to 0.
Yep. Then you have sk minus t is equal to bk. So your sk's are going to have to be different because your bk's are different.
Yes, but I mean, yeah, all my sx. I mean, I know that my s will have some values, but I know that at least one will have the value 0.
Oh, I'm sorry, I
misunderstood. For this particular sk, I know that sk will be equal to 0, and this means that I actually found a point, which is feasible because it verifies this constraint. So this is not the standard. This is the auxiliary problem constraint. I found a particular point, which is a basic feasible point because I have lots of zeros. Basically, I have n plus 1. Sorry, I have not n plus 1, but I have n minus n plus 1. Rather, anyway, the right amount of zeros so that it's a basic feasible point. This thing can be solved as a simplex with the simplex algorithm, because really it's the simplex algorithm starting with a feasible point. The only difficulty you had, you are going to run your algorithm on this problem, and the nice thing is that you are going to get an optimum value for t, and it's very simple. It's t is if t is positive, it simply means that the problem is not feasible, and you don't really have to worry anymore about solving it because you have 0. Your polyhedron is empty. There is no point in the universe that satisfies the constraint. Otherwise, like probably in the assignment, you're going to get t equal to 0, which means you have actually reached a feasible point. And from here, you can either get the identity submatrix, to know on which point you are. You remember, so from the tableau you can know where you are on the polyhedron, or if I am not mistaken, much more simple. You have your tableau, and let's suppose this is the column for t. You just drop it. And if you just drop it, you get immediately the tableau for the simplex algorithm, but the tableau starting from a feasible point. And then you can rewrite the algorithm and get what you want. Okay. And I had, okay, so this concludes the part about the technical difficulties. Oh, yes.
Yeah, can I just add something to here? So if you're going to do the deleting the column method,
Yes.
well, actually, in either case, you should carry around the costs from your previous, the original costs.
Yes.
Instead of this one, you need to carry it around with your Tableau and perform the raw operations on it as well.
What do you mean by the cost?
So you had to minimize C transpose X or maximize C transpose X or whatever.
Yes.
That's the original problem you're trying to solve. That
Yes.
would be your phase 2 cost.
That will be the yes. Okay.
Or objective
Yes.
large or whatever. In phase 1, you're introducing this new one.
Yes.
But any row operations you do to minimize this new one, you need to also perform on the cost vector so that it reflects the change.
Oh yeah, you mean this particular row? This is the no. This is the thing you're trying to optimize.
The row that would otherwise be your cost row,
Yes.
you need to treat as a constraint.
Well, you can't pivot on it.
You're right, you can't pivot
Yeah,
on it.
yes.
You need to do row operations on it.
But is the operation you would have done normally, right?
Yeah.
So okay.
Yes, but it needs to be in the Tableau for the phase 1 portion.
Okay.
as
Yes.
well.
Okay. Any other question? But thanks for the question. I just had a very short, I believe, I hope, very short notice about some interesting properties about the dual of the problem. So, some math that you normally have seen in course. So, let's suppose I divide again my space in some bases b and the rest n. So, I have bn. And so, I have x is equal to xb plus xn. So, as I told you, you can, in fact, entirely determine xb through this. Oh yeah, so bn such that matrix LB is full rank. Well, it's full rank, it's rank n. AB minus 1 of b minus an xn. The interesting thing is that now you have C transpose X. What you're trying to maximize is thus you can separate the same way you separated X in XB and XN. You can separate C in CX and CB in CN XN. Through some computation, you can get okay. I'll give you directly the simplified result, which is B transpose Y minus SN transpose X XN with, so Y is equal to, this is minus transpose, by the way, inverse of the transpose, and SN is equal to okay, so one important thing to note is that, first of all, B, Y, and Sn do not depend on the choice of X. It only depends on the choice of the basis. You look, what am I writing? Sn is a newly introduced parameter. No, S actually depends on Xn. What am I saying? No, sorry. Yes. Sn and Y are newly introduced parameters, but entirely depend on the things you knew from before. They are entirely described here. They do not depend on X on any way. They only depend on the matrix. On the choice of the basis. And now, so this is what you are trying to optimize. You want to maximize C transpose X. And the thing I wanted to introduce is that, in fact, when you have a basic feasible solution, which in our case means that you found a B such that xb positive and xn equals 0, and you consider actually this problem, what you may notice is that if Sn is positive, there's no way you are going to be able to increase this. And this means that you have reached actually the optimal value. However, if there is if there is a k belonging to n such that sk is strictly negative, you have found a direction where you can increase the the things you are trying to optimize. Okay, so this was just a short presentation on how the linear algebra we saw at the beginning kind of matches what you see inside the Tableau. So this really means that when you rewrite the whole thing, through y and Sn. You just need to look at the Sn is really the row on the bottom, and you're trying to look at, with a minus sign, sorry, you're trying to look at the directions of increasing step. Sorry, increasing, yeah, it's called step, doesn't matter. Well, the direction in which you're going to increase what you want. Okay, and now, sorry, this is getting a bit long. It was really short introduction just to say that a linear program has got a dual, just the dual problem, which looks highly like the first one. Yeah, sorry. So this is a C, and this is a 0. This is the dual problem, and this is just here for purely cultural reasons, why it may be interesting for you. As you can see, this is once again a linear program. It happens. In fact, it seemed to happen more frequently than not that this problem is simpler to solve than the original problem. Like I personally know that in the traveling salesman problem, it's simpler to, well, with additional cuts, it's actually simpler to solve these versions. And just in general, it should be the dual of the linear program happens to have some. Well, it's just simpler to solve, and you should always check when you're solving a problem that is in fact not much easier to solve the dual. Yes, you had a question.
Yeah, I guess if the primal is just the dual of the dual.
Yes.
So couldn't you just say for any dual problem you have, it's easier to solve its dual versus primal?
No, it's not the case. It's just that when you model the problem as a it's not the dual is always simpler to solve than the primal. Is that the way we express problems, like string problem with cuts, we have discovered that when you go to the dual, it's actually much simpler to solve just in terms of computing time.
Right. So I was to say that if it's the case that in general the problems we come up with, the duals are easier, and it's not the dual with the primal is easier. Yes. It must be something having to do with the ratio of n versus m. And so, so what is it? Are most problems, they have a lot of variables, so they're high in n, or they have a lot of constraints high in n?
So yes, as your question more or less implies, it's that when you take the dual of a problem, you are switching variables and constraints together. Variables becomes constraints, constraints become variables. The problem is that I would not like to say something that may be totally false, so I prefer to abstain from it.
My intuition is that the more constraints you have, the easier it's going to become.
Well, with the exception of the fact that if you have a lot of constraints, you have a lot of vertices. So, and you can get a lot of vertices really close to each other, and it can really slowly converge to an alpha.
Right, but I think that, so the reason I have this intuition, right, is because if you have more constraints, you have less feasible points.
Right.
Right?
Yes.
So, in some sense, if you only have one, like the extreme case, if you have exactly one feasible point, the problem is trivial.
Yeah, it's exactly fine.
Right.
Yeah. It might be, yeah. No, in fact, it might be totally right. I would not dare to tell you that it's actually
it's not
the reason.
Space, right? For the number of vertices.
Well then.
Independent of that as well, I think it also makes.
Sorry, but I just wanted to say that I believe this is over. Thank you for your attention, and well, good luck for your assignment if you haven't done. Thanks.
One last announcement is that the next session's on Tuesday on approximation algorithms, not integer programming. Integer programming will come after approximation algorithms. Okay.
The other reason that this would make some sense is you have to compare these.
Thank you.